Thank you, Dr. Klin, and thank you, Hadassah. So I'm going to repeat that just the exact similar method and code to quantify current density. So Hadassah make the life easier for me and cover all theory. So next, please, Dr. Klin. So previous week we covered the ab initio exact state dynamics based on non-adiabatic coupling. So for my model, if Dr. can go to next slide, I have a conjugated polymer, as you can see on the right, next to a acceptor unit. So here, actually, this previous project, the model was actually the interface or the charge transfer was explored in the z direction. So the bottom actually chemical structure is DPP polymer, and the top one is PCBM acceptor unit. So to quantify the charge transfer, last week we just measured the difference in the middle figure, the difference between the positive and negative charge, and actually define it as dipole, and the derivative of that dipole gave us the current density. So, but in this presentation, we are going to use another method as Hadassah presented. So, Dr. can we go next? We can skip this. I had to delete this one. Yeah, as you can see in the right, the difference between positive and negative charges gave us the dipole, and the derivative of that dipole gave us the current density. So in that project, we use maximum value of this current density to quantify the current density and also characterize the best photovoltaic system with better actually power conversion efficiency. Next, please. So in this presentation, we want to use continuity equation. I don't want to go through that much. Hadassah already fully covered that. So here in this divergence operator, actually we skip the x and y direction, since the charge transfer is supposed to be done in the z direction. We have just that operator applied to the current density just in the z direction to quantify the current density as an integral of that equation. So the parameter g is something that we are looking for. Next, Dr. Kiran. So to run that code, if you go to the MATLAB directory, you can find the charge density on the line 7. As Hadassah mentioned, just need to tweak the minimum and maximum orbitals mentioned in the energy gap. Also, you need to have the RRR file that we review how to calculate that last week. Also, you need the band out file. Next, please. Yeah, if we take a look through the in the left, the yellow color represent the electron and blue represent the holes, and based on the continuity equation for DPP PCBM, we can have the current density as the right figure. Here's the positive value means the electrons move in the positive direction, and the negative value means that electron move in the negative direction actually. And next, please. Here you can again in the right, you can see that the amount of the charge transfer at the interface at the different times, the hole which are transferred and the electrons. Next, please. And here, if we just take a look through the absolute value of the current density, also in the next slide, we have the comparison of two methods. Dr. Kenan, can we go next? Yeah, here the top results represent the the current density calculated by derivative as a derivative actually of the dipole over the time, and the bottom one is the current density calculated by continuity equation. So for if I want to compare top and bottom, so in time logarithmic time of -1, we have a peak, but the maximum value for these two methods is appeared at different times. So usually we have the same location, same time for the peaks, but the maximum value at different location. In addition to this, I'm not sure, Dr. Kili, how to interpret that or how you can find any other connection between these two methods. Can you please share also your feedbacks on this plot? Or does it make sense to have a absolute value of the current density when we are using continuity equation?
So if one would make an average over the neighbors, like smoothing function, then this sharp maximum will disappear. So the main amount of charge is transferred at the same time.
Yes, after smoothing data, if we ignore the each moment, yes, that's the point.
Quite encouraging what you are showing. And I would try to find proportionality coefficient and just show them not in different panels, just on the same panel. Find a scaling factor which will make them as close as possible.
Sure. Okay. Yeah, definitely. I will do that. And yeah, that's the last slide. So thank you. If you have any question, I would be happy to answer, if any.
Okay, please join me in thanking Amir. Any questions in the audience?
Yeah, I have one.
Okay, yeah, please go ahead.
So if I understand I guess the general idea is, the assumption is the charge transfer will happen in one direction. That's why you guys assumed it in Z. Just out of curiosity, how much more calculation time would it be to simply just have all three? Or what makes it so much more complicated to do all three dimensions?
I didn't get exactly your question. Why we didn't explore a 3D system? This is your question?
Yeah. Yep. And I guess the main question is how much more time would it take to do all three?
Yeah, thank you for the question. This is actually something that we are working on right now. So at first, we just develop a periodic model for the polymer and put just one acceptor unit next to it, and also develop the interface in the Z direction. So this is a very idealized periodic model for this kind of bulk heterojunction. But for the project that we are doing right now, we developed a condensed 3D periodic DFT model. So we packed multiple chains and acceptor units, run with force field calculation to reach to the kind of density, experimental density values, a completely packed system. And then we are running non-adiabatic couplings. But for sure, those systems are 5 to 10 times larger in case of number of atoms. So each system, each aspect of that cubic is around 3 nanometers. So they are pretty expensive and challenging models. And we are thinking how to actually quantify the charge transfer for such that 3D systems. For sure, this kind of approximation or idealization will not work for that 3D model. So we need to find another way to visualize or to quantify, actually characterize the charge transfer between the donor and the acceptor unit in the 3D system.
Yeah. Okay. Yeah, that clarified it. Thank you.
Can I add to this discussion?
For sure. Please.
So on one hand, 3 comments. First, actual quantum dynamics can be processed independent on the direction of charge transfer. The question is that we raised and Amir supported is about interpreting the pathway of charge transfer when it deviates from single direction. And next talk will partially address this question. But from industrial point of view, most devices do have like one anode and one cathode, or the solar cell or diode have two terminals, and the charge transfer in a selected direction is typically much more important. So therefore, analysis of charge transfer in one direction is valid and important, even if the system shows more rich behavior.
Mm-hmm.
So it's all an opinion. More questions in the audience? More questions online? Someone is typing. Aaron, would you like, Amir, would you like to read question by Aaron and address?
Sure. Aaron asks, to quantify charge transfer, could you project Kohn-Sham orbitals onto the time evolving density? I do not have a certain answer for Aaron, so it should be doable when it comes to your mind for sure. Can you provide more comments and tips, Aaron, if you think it's useful for this project?
It looks like Aaron's question is, in a good sense, provocative. He pushes us towards the next talk. In some sense, what Amir is showing is already projecting Kohn-Sham orbitals onto time evolving density just in one dimension. And the question is, can one go into like 2 or 3 dimensions? Aaron, is your question interpreted correctly?
Yeah, but I think, wouldn't there be like a numerical way to do it? Where you could like multiply like occupied and unoccupied? I don't know, I'd have to think about it more how to phrase it.
Okay.
But essentially, like, instead of projecting orbitals, projecting charge density in like whatever grid you're using.
Okay, so instead of population of orbitals, write an equation of motion for charge density distribution.
Right.
It is very possible, but it will be much more expensive because amount of grid points for 3-dimensional distribution is substantially bigger than amount of discrete orbitals that we are pursuing.
Right.
So if we are propagating like 100 orbitals, and there even a humble system has about 1 million grid points, or at least 100,000. So it will be different level of numerical complication with about the same output.
Mm-hmm.
But in derived equations, it is very appropriate, and some people write density matrix equation of motion not as matrix in discrete basis, but as a continuous density with 2 independent indices. So as a method for theory for equation derivation, it's quite popular.